So once again, welcome my dear friends. The second segment of solar PV, MPP and MPPT algorithms. In the past lecture, we hurriedly discussed about how we can introduce the duty cycle in the converter section that is connected with the solar PV. Now we are going to introduce the maximum power point tracking algorithm. So these two small modules we have done, that is act as a prerequisite, because those who have already covered the aspects of power electronics, they must know how the duty cycle are going to be have a heart of the converters, means it's the incorporation of the duty cycle in these converters, how the voltage will be changed, or specifically the rise in voltage in case of boost converter and decrement in the voltage in case of buck converter. Now we shall begin with the concept of MPPT with simulation analysis, MPPT algorithms, how to design the inductor and capacitor, various converter topologies, and if we can go with the new adaptive algorithm, then how we are going to implement with the solar. I shall try to demonstrate this thing with the PSIM software. So in the introductory part, we have completed this maximum power points. Now we need to track this. So over here, a buck boost converter, the same diagram is there, but in the real world, this is connected with some load. That load is now AC in nature. It might be AC or DC, but in majority of the cases, AC loads are available in day-to-day life. So we are connecting these converters with the inverters also. So again, when the switch is closed and when the switch is open, in both the cases the uninterrupted power will be reached from source to the load end or at load end. So from the equation in the output section, that's what it's a revision of the past lecture, is the ratio of D upon 1 minus D, that is equals to output voltage upon input voltage. And I tried to explain the same thing with the example. This example proves that we have taken this as a boost converter. It concludes the same thing by considering two aspects. Our output voltage is more than the input voltage. Over here, it's a boost converter, and our duty cycle, second thing, our duty cycle is above 0.5. So if we can now conclude this prerequisites, so this is what the change in the voltage in current with the change in percentage duty cycle. So now I'll start a demo of the simple buck converter in the closed loop manner. So we have designed the inductor and capacitor. Lots of online converters are available. And in this case, I have used online buck converter, boost converter, and buck boost converter calculations, authored by Michael Green, published by Texas Instrument Incorporation. So what we tried to do is, we are having some input voltage over here. This is the configuration of buck converter. One diode is provided to not allow the reverse power flow, LC tank network, load, and some measurement units. We also have a closed loop converter. So in that case, we are sensing the voltage from the output side, and we are comparing that voltage with the voltage that's what we want over here. Then it is connected with the PI then we are having limiter, and we can select the duty cycle which is either 0.5 or above 0.5, and then we will generate the pulse. This entire simulation is connected with 10 ohm resistance, and another 10 ohm resistance is connected in parallel, and I have tried to given the same thing with the time logic, means after some time this load will on to check the effect of this closed loop system. So our input voltage is 100 volt and our reference voltage is the 50 volt. So if you can check this 50 volt over here, at that time we get the straight line at 50 volt, and this spike shows that after half time, suppose the simulation time is 1 second, then after 0.5 second this load is introduced. So this is how the buck converter works, and this is what the pulse of the buck converter. We are having the pulse train of the same. Now we are going to introduce this kind of techniques, as I have tried to demonstrate the buck converter first. So these buck converters which are connected with the PV is usually used to charge the batteries, because what happens generally in the battery, whenever you will have buck down the voltage, at that time the current is increased in the output side. So as the current is increased in the output side, the battery will charge in the more faster rate. So this is what the advantage. So let's take a practical example. If we are having the 17 volt PV voltage and my battery voltage is 12, and if I buck the voltage from 17 to 12, at that time the current in the output is marginally increased. So I'll get the more output current if we are having the buck converter. This is what the basic concept or the truth behind the buck converters used for the battery charging applications for the photovoltaics. This can be also used for the wind energy conversion system, but in this session I tried to cover only the significance of the photovoltaic only, means MPPT on the photovoltaic only. So if you can have the MPPT techniques for solar energy conversion system for particularly PV, these two techniques are well known across the globe. The first is the perturb and observe. Perturb means the interruption and observe means the effect of interruption. It is known as P and O technique. The second is the incremental conductance technique. It is also known as INC technique. So before proceed further, let's begin. What is the concept of MPPT? So if you have gone through the lecture where we have incorporated the DC load, so in that case the operating point on the IV curve was the concept. So let's revise this concept. The operating point of the load is the point at which the IV curve of the load and the IV curve of the PV intersects. So in this case the power from PV module will vary in the case of irradiation of the sun and the temperature and some other climatic conditions such as moisture and dust of the atmosphere. Due to this reason, it requires to continuous tracking of this optimal power points, otherwise it will track only suboptimal points. So the intersection of the load characteristic will not track MPP. So MPP has to track with the change in atmospheric condition, and this thing has been demonstrated in this figure. So in the first case, this sky blue color line is the IV curve, the red color line is PV curve, and we need to track the point. So the pink color line shows the behavior of ideal curve, but every time the ideal curve is not like this. If it is actual load, say for example rheostat, this might be this line. So we need to track this power. It can reach over here, which shows the maximum power hyperbola on the IV curve, and it will track the maximum power. So every time your load is going to be changed. So suppose this actual load is over here, now it might be over here, it might be over here, it might be over here. So at that time we can track this power. So for that the maximum power point tracking algorithms are used. See guys, there is no magic in this. We are just playing with the impedance matching game. If you can go back into the fundamentals of maximum power transfer theorem covered in the undergraduate program of electrical engineering in network analysis subject, you have a concept of RTH equals to RL. So at that point the maximum power is transferred from source to load. So this concept is used over here also, but that concept is there for the fixed load. Over here the load is variable in nature, the source is variable in nature. Again you can have a source, we can subdivide it in terms of the radiations and the temperature. And as we have concluded in the last short video that the radiation and the temperature both are changing simultaneously. So the radiation largely impacts the short circuit current of the PV module, and temperature largely impacts the VOC. So you can redraw all the curves if your climate will change, and at that time your load will also change. So there are three possibilities: radiation will change, load and temperature will be constant. So there are three factorial things you can introduce. So it is not our cup of tea right now. I'll have a more video session in the coming days on this, but the main thing is that whenever we are introducing this thing, we need to track this point, and this is your maximum power point. The algorithm needs to track this point, known as maximum power point tracking algorithms. So this is what the points that I tried to explain. So this is what the block diagram for MPPT algorithm in the closed loop manner. So we need to reach over here. So for that we are having the solar PV module, we are having a voltage and current. We can sense the voltage and current that has been fed to the MPPT algorithm. Depending upon the selected algorithm, the reference voltage or reference current will come out. It has been compared the actual voltage or current. In this case it's a voltage based MPPT algorithm. The error signal is generated and it is given into the controller or any controller. In this case it might be a PA controller, and then we are having the modulator signals. It will generate the duty cycle and my switch will operate, and the power is transferred to the DC load. So this is what the block diagram for MPPT algorithm. So if we can have a same concept with the circuit diagram, at the initial part, what is the concept? The concept is PV module is connected with the rheostat, and this curve is well known to us. So if we can increase the resistance, my current will go down and I will try to approach this VOC point. If I will decrease the resistance, the current will increase, I will reach at ISC point. But this is totally uncontrolled. So to provide the same thing, this is what the thing that has been plotted only for IV curve at the various value of resistance, and you need to track this RL, that is R optimum point, through algorithm. So basically there are two types of MPPT algorithm. One is the mechanical tracking where we are having a DC motor and the panel itself is reoriented with the change in direction of the sun ray or the sun itself. And the second is the MPPT, that is what we used for the interfacing the load and the solar PV. So the thing is that we are going to introduce the power interface over here. In the previous demo it was the buck converter, if you remember, and over here it is connected with the load. So what we are trying to do, we are keeping input impedance fixed. We shall not vary it, and we are changing the output impedance. So by having the permutations and combinations, the optimal point will be reached within the input condition, and my output power will be vary with the change in load. So this is what the reflection of load. Over here we are having the input impedance RT seen by the module, it is fixed, and we shall track this optimal power point with a straight line as 1 upon RT, and similarly that point has been again plotted as X on the screen on PV curve. This figure I have taken from one of the renowned professor's lecture, Professor L. Umanand, IISc, Bangalore. You may go through the lecture on the concept of MPPT by Professor L. Umanand also. So thank you, sir, for providing us this information. So let's proceed further. So now how this P&O algorithm works. So at that time you can take any of the point on the PV curve in this case, and you can check this whether the system approaches towards MPPT. If your answer is no, then you need to introduce one more increment in the perturbation. So your characteristic equation will be the reference voltage equals to your sample you have selected, suppose it's a kth sample, plus or minus C. That is what the perturbation size we are going to introduce. Now as far as perturbation size is concerned, so at that time if you can check, if my perturbation size is more, then my output voltage is also having the considerable value. So the equation might be your reference voltage equals to reference K minus 1, that is past iteration, plus or minus C, where C is the perturbation size. To select the perturbation size, if you go with the higher perturbation size, you will reach at this point within short time. Suppose I will select from here, I will select this perturbation, this and this might be any digit, but our accuracy is less. If we go with the smaller step size, then the perturbation size is less, accuracy is high, but it will take long time so to reach that MPPT. So the concept is this concept is known as perturb and observe. So if you can have this flowchart of algorithm, as we have sensed over here, the voltage and current, this voltage and the current, it has been sensed and it has been given to this MPPT algorithm. Then we should introduce the power. The power equals to V into I. So in this case, if power equals to V into I, this is our current power, this is my past power. If it is the same, then we are having the same duty cycle or same reference voltage and hence duty cycle. If it is no, then there are two possibilities. If this difference, present power and past power, greater than 0, or present power and past power less than 0. If this difference is greater than 0, then there is decrement in the power. If greater than 0, then it is increment in the power. From this point onwards, you will find n number of research articles, papers, book chapters in the internet world where people are also tested these algorithms in terms of voltage and the current. This is the flow chart of voltage as a perturbing variable. So if this condition says that no, then we'll check it for the voltage. If my previous voltage and the past voltage, means previous voltage is greater than the past voltage, if yes, then we need to decrease the V reference by certain perturbation variable. So what is our equation? What I spoke, V reference equals to V reference k minus 1 plus or minus c. In this case, the minus c will be introduced over here. In this case, the plus c will be introduced. If we can go back over here, if it is yes, then Vk minus 1 greater than 0. If it is no now, in this case if it is yes, then we can decrease the reference. In this case, if it is no, then we can decrease the reference. And similarly, we can increase the reference voltage, and then the algorithm will be returned to its original state. So this loop will rotate every time once your climatic condition will be changed. Say for example, somebody can say that what if the radiation will change? Ultimately this P is borderless V and I. V and I, that is voltage and current. So in both the cases, the voltage and current, ultimately the power will change. So the results in this 4 possibilities. So our next concept is the incremental conductance algorithm. So in incremental conductance algorithm, over here change in voltage has been measured, and if you can go with the PV curve of the PV module, we shall go with the dP by dV, that is the ratio of power upon voltage and its derivative. If it is equal to 0, then we reach that MPPT. If it is greater than 0, we are having the left side of the PV curve, its left side of the PV curve not at MPP point, and if dP by dV less than 0, it is the right side of MPP point. So if we can go back again, this is the flow chart of incremental conductance algorithm. So again see, again it's a voltage base. Our outcome is same, but the method is different. So if we can sense voltage and current, we'll have a delta V and delta I. So in this case we are having the conductance, it is the ratio. See guys, in ultimate case the current of the PV module is less compared to voltage, and if you go with the ratio of I by V, again it is still less. So you will get the accurate result of MPP points. In the latter section of this lecture, I shall try to introduce the basic difference between these two techniques. So if you can check the voltage perturbation, if it is current perturbation, then delta I equals to 0 in this case. So if delta V equals to 0, if it is yes, then we will check with the delta I. If both are yes, then the algorithm will return there is no change in the climatic conditions or the load. If it is no, then this I plus delta I by delta I, that is very important over here. If it is yes, then this fraction is very small, so again we can return. But if no, then we'll check that whether it is in greater than 0 or less than 0. If it is greater than 0, then we can increase the reference. If it is less than 0, then we can decrease the V reference. In similar way, if you go with the delta I greater than 0 or less than 0, because over here once we have introduced the I by V term, only we will check the delta I over here. So if this condition says no, then it must be greater than 0. somebody can say that, sir, what if it is less than 0? So less than 0, again it will come into the same segment and your algorithm will be written. In similar case, if it is yes, then again it's a reverse of it, increasing the reference, over here decreasing the V reference. So this is how the incremental conductance works. So now we can introduce this di by dv. If di by dv is minus 1 upon v into I, that is I by v ultimately, so it is our MPP point. If it is greater than minus I by v, this left of MPP, and if it is greater than minus I by v, it is right of MPP. I am sorry, it's di by dv greater than minus I by v, it is left of MPP, and less than minus I by v, it is right side of MPP. Ultimately our power is v into I. So now let us begin with the demonstration of algorithm in the PSIM software. The same converter I have used, that is the buck converter, but now this buck converter is connected with the photovoltaic module and the battery of 2.24 volt is connected. Now before proceed further, the bottom and observe algorithm is used for the gradually varying climatic condition, and incremental conductance algorithm is used for fast changing algorithms, means fast changing climatic condition. It means that the locations where the radiation changing is in very fast manner, radiation, temperature or the load, but particularly radiation and temperature, people will prefer incremental conductance. However, in this case people will prefer the bottom and observe where the gradual change in radiation is there. Moreover, as we have a particular perturbation size, we reached at MPP point by having adding or subtracting the particular radiation pattern or a particular radiation format. We are going to introduce the perturbation constant C, or we can say perturbation size. So that perturbation size is known as perturbing variable. So you will find lots of articles also how to select this perturbation size, because usually if you are considering the voltage and you are changing the radiation, obviously the impact of the radiation on the voltage for the photovoltaics is less. So we are selecting 0.1, 0.05, 0.2 as a perturbing variable. So now over here the square wave is given, that is the change in the radiation pattern, and that pattern remains fixed and 25 degrees centigrade. So over here we are introducing the perturbation variable, and we are going to introduce this PV panel in the PSIM software. We are having the voltage sensors. Over here it's a perturb and observe MPPT algorithm, and over here the battery is there. The reference voltage is selected from this segment. I'll try to demonstrate you, if you will change the input parameters, then how this MPPT shall not track. First we will check how it is tracked. So this is what the maximum power from here available from PV, and it is superimposed on the power generated by the PV. So it has been almost tracked. So such algorithm have effectiveness above 98%. That is known as the tracking efficiency. Similarly, instead of the single module, if you go with the 4 number of modules that is connected in series without changing the reference, then this MPPT detract from its original position. Similarly, if you again set the reference and set the PI controller parameters, your efficiency would be again retrieved. So if you can see the case over here, a 60 watt module, over here 240, means 4 such modules are connected in series, and we are harnessing almost 230 to 240 watt power. In this case we are assuming that the converters are ideal in nature. So if you need to introduce the basic calculations of this stage, there is a data sheet of Michael Green. Michael Green is the author and it is available online. It is introduced by Texas Instrument. So from that you will decide your input voltage, input current, output voltage, output current, depending upon the converter configuration, and efficiency. How you can measure the efficiency? It is estimated as 80%. Usually converter efficiency is more than 80% because they all are static in nature. So from this equation you may also find out the inductor value, and you may also find out the value of the capacitance. So now we can demonstrate the same thing with the boost converter. So for starting the same thing, we shall plot the various IV and PV curves of the module, that what we are going to target. So this is what the input parameters that we are going to introduce in the PSIM model. This is what the various IV and PV curve with the change in radiations level and the temperature level. And then with those equations of L and C, we found out L and C of the boost converter. So the block diagram of the system is like this. This is the photovoltaic part. These are the sensor parts. This is our boost converter. Watt solar is the wattmeter. That's what the power has been drawn by the load, and this fourth stage is the load section. So PV, from where you can sense the current and the voltage, then a converter stage, so it will be boost up. It's a basic configuration of the boost converter, and over here we try to measure the pulse, and then we are having the voltage in the output side. So again, this calculation the same in the one slide I tried to introduce. You may stop the video or you may download the sheet while calculating the same. So case 1. The case 1 is the standard test condition, means the input of this diagram, we are having 1000 watt per meter square radiation and 25 degrees centigrade temperature. It has been fixed, and my R is 20 ohm. In the previous section we tried to demonstrate with the change in radiation. In this lecture I tried to demonstrate the same with the change in the load pattern, means my radiation temperature is fixed and my load is 20 ohm. So this is my output voltage, module voltage with the red color, output voltage with the blue color. With having the various fine tuning parameters of the PI, you will get the straight line over here also. This is what the tracking effectiveness is. This is the power drawn by the load, and these are the pulses. Again, this graph might not be a straight line because I tried to plot the transient mode of the system. However, in steady state mode, you will get the good quality of the voltage levels. Similarly, if you because in this case we are actually checking the MPPT effectiveness, we are not checking the quality of the graphs. Again, if you increase the load current, means decrement of the resistance, see the boosting level has been decreased, still it has been tracked, and this is what the power. So power is reduced in this case because the load demand increased, so there is slightly reduction, because afterwards if you have a very less amount of resistance, this PV might not may feed the power according to the requirement of the load. So people prefer rheostat to test this PV module. Again, if it is 10 ohm, these are the various conditions, but see the boosting level, it has been dropped, and for 5 ohm, see it's almost negligible for the same. So 3.29, the boosting level is not there, but still it will track the maximum power somehow. But if you can check the pulse, our pulse is 0. It means that over here, below this, the power cannot be fed, and this might be our RL, RTH equals to RL condition, but the converter was not present at that time in our mind. Now the next case, if you can reduce the radiation, that's what we have done for that perturbation, 1000 watt per meter square to 800 watt per meter square. We can change it from 800 watt per meter square to 600 watt per meter square. At STC means your temperature is still 25. There is no change in temperature, only radiation has been changed. Remember this, at STC in the case 1, this 1000 watt per meter square to 800 watt per meter square, we have checked. Why? Because the perturbation is too introduced, otherwise the algorithm cannot suitably work. So this is the module voltage, the boost voltage. This is the radiation pattern we have followed. This section, this is my output power. So it is reduced compared to what between 1000 watt per meter square to 800 watt per meter square. This is what the MPPT tracking efficiency. This is our maximum power, and this blue one is our track power. In case 3, we are keeping the same thing, but now we'll change the temperature from 25 to 40 degree. So again, the slight decrement in the efficiency, slight decrement in the boosting voltage. This entire thing can be done at the 15 ohm resistance. Now if we can compare with MPPT and without MPPT algorithm, so in that case our comparison is in terms of this. If it is with MPPT and without MPPT, in that case we are having a 0 boosting over here. We are not going to track anything that is going to be because the algorithm is not existing. If you can again use MPPT, see the power output has been tracked, and you will get the significant amount of power. Over here, some of the power is already drawn by the load, but the efficiency, we are not getting that maximum RT point. That's what we discussed earlier. Similarly, we can go with the boost converter stages for the same. That's what we used. So if you want to do some work at your homework, you can design your LNC of your own choice level. That's why it has been reintroducing right now in this slide. So now I'll try to explain the same thing with example, because we have started in the last lecture for buck boost converter. So in converter we are having some range. So if our range is 8 to 40 volt, so in that case our output voltage we are expecting is 15 volt regulated. Our switching frequency is 20 kilohertz. Our capacitor is 470 microfarad. So we need to calculate the minimum that the converter will be operating in the continuation conduction mode if my output power is greater than or equal to 2 watt. So let's begin the example. So our input voltage range is given, output voltage range is given, switching frequency is given, P0, that is power expected, highest power is 2 watt. Then we can find the current by having the ratio of P0 upon V0, it is 0.13, and our R equals to V0 square upon P0. Here we are taking V0, so I will take 15 over here. Keep this thing in the mind. Now the duty ratio for input and output voltage, we are having equation D equals to V0 upon V0 plus Vin, that is equals to 15 divided by 8 plus 15, it's 0.65 for 8 volt. For 40 volt it is 0.27, so that is the range of duty cycle. See, this buck boost converter from 8 to 15 it is in boost mode, 40 to 15 it is in buck mode, so we are having the huge range. of the duty cycle, means in both the way it will operate. And the equation of inductor is 1 minus d square into r divided by 2 into FSW. And we can calculate, say for example, for this 0.25, and from the equation of power we have also calculated the resistance from this, so it is 1.49 millihenry. So this is our minimum value, and from this equation you might also find out, extended to this problem, C out minimum, that is 1.17 microfarad. However, such kind of capacitor might not be available into the market, so in that case you may take the nearest value of the capacitor that is used. Now this is an example of step down converter. So in step down converter we can consider the all component to be ideal. Our problem statement is expected output voltage is 5 volt and the range is now 10 to 40 volt. The switching frequency is now increased as 50 kilohertz. The power output expected is greater than or equals to 5 volt. So we have R over here, this V0 square, expected output of 1 P0, get the 5 ohm. So the duty ratio D would be V0 upon Vin, that is 5 by 10 equals to 0.5. So this duty ratio for output voltage of 10 volt, this is for 5 volt, 5 by 10, this is for 5 by 40. Sorry for this, the output voltage for 40 volt, it is 0.125. So over here 0.125 to 0.5 is the duty cycle, and the minimum inductance accordingly is 38.21 microhenry. Similarly, C out minimum is 2.5 microfarad. See, the switching frequency is also we need to change as per the equation. So these are the two examples. Now we are going to connect the PV with DC load and the incorporation of the MPPT algorithm. That is our final segment. So when the PV array is connected with the DC to DC converter and the load, through block diagram I tried to explain you how you can incorporate the control method and then PWM by generating the duty cycle. Over here duty will be over here instead of here, so we can control this DC to DC converter. So in this case, in the previous case the same diagram was there for the voltage perturbation. This is the adaptive control in the case of the current perturbation. This block diagram I have taken from one of the research paper published in 2014, that is adaptive control MPPT technique. It is in IEEE transaction, authored by Professor Satish Kumar Kolamila. Similarly, if you can go with the same thing, we have to code that algorithm and then we'll check the other things in terms of input and output. So this is what the code has been there in the DLL block. We are having the input, we are comparing this part of an observed variable, that is reference current. Previously it was reference voltage, so this is now current perturbation algorithm. And then this is our PV section as usual, this is our sensor section, this is our MPPT section, this is our control logic, this is our boost converter, power measurement unit and the load. This is what the result analysis. The result has been done and analyzed for 250 watt module. And this is what our maximum power, as the reaches of the power is due to the perturbation applied in the square wave fashion in the input. Similarly, we are having the power from the power drawn from this wattmeter, and we get the actual voltage and the boosted voltage. So again, if you can compare the same thing with MPPT, without MPPT, see the change in power that has been shown. So by connecting this switch with the ground, this MPPT algorithm will be bypassed. You will find this result. Now, when the PV is connected with DC load, over here we have tried to demonstrate the boost converter and buck converter topology. That is in the section of the isolated converters. People may also prefer to use the non-isolated topologies. The isolated topologies are boost converter, buck converter, and the buck boost converter. In case of non-isolated topologies, they are flyback converter, push-pull converter, half bridge, full bridge, and the forward converters. Now, I'll try to demonstrate the adaptive one. So this is the algorithm I was talking about. I did author. This thing is part of an observe, and this thing is newly introduced. I'm thankful for the author for providing us such efficient algorithm to generate the maximum power point methods. So this thing we have introduced in the solar PV modules with the boost converter. The error is given to the PI controller and limiter, and we have triangular voltage waveform is given to the boost converter, and we are getting this results for the same algorithm. That's what we have done. Similarly, if the multiple modules are connected in series, then this is the simulation analysis for the 30 modules of 60 watt each connected in series. So we can have 1800 watts, 1.8 kilowatt power output. This case. So thank you very much for your patience listening. In this session, I tried to cover all the aspects of maximum power point with its importance for the solar PV, how to track the maximum power point using voltage and current and the perturbing variable. I hope you enjoyed the session. I am very much thankful to all the authors, those who have published good research articles and good online lectures for the same. And I am also thankful for all the listeners to listen this session. Thank you very much.